continuing our discussion of adding vectors, we're going to now look at adding vectors through component form. If you don't recall how to resolve a vector into components, now would be a good time to go back and review the video on resolving a vector into components. Recall from our previous video the two vectors that we used, vector A, which was 20 newtons of force directed at 45 degrees to the x-axis, and vector B vector B, which was 40 newtons of force directed at 135 degrees to the x-axis. And our resultant vector was given by the composition or the addition of vectors A and B. Also recalling that the results of our graphical methods, this is the result from our parallelogram method and our tip to tail method. And while we can get an approximate magnitude and approximate direction for the resultant vector, we see indeed that it will be in quadrant 2. And that's going to bring up a concern with our mathematical calculations of direction in a moment. It does not give us exact values. And so before going any further, it is going to be necessary that you make sure you understand how to resolve a vector into component form so that we can compare this to our graphical results. Looking at the component forms, we know that the x component of a vector is given through the cosine function and the y component of a vector is given through the sine function. However, since we're dealing with two different vectors directed at two different angles, we now have to include some subscripts. And theta 1 now refers to the angle of vector A, and that is 45 degrees. Theta 2 refers to the angle of vector B, and that is 135 degrees. Performing our relevant substitutions here, you should be able to ascertain where these expressions came from. You have the magnitude of vector A times the cosine of 45 degrees, or the cosine of the angle that it makes with the x-axis. And then you have the magnitude of vector A times the sine of 45 degrees, or the sine of the angle that it makes with the x-axis. And then I will leave it to you to ensure that you can arrive at the expressions for vector B. Substituting in the values, before we do our substitution, we need to look at the bottom here and develop our values for our sine and cosine functions for our relative angles. And we do see that these are highly repetitive numbers. Indeed, that's where the concept of the unit circle arises from. And you see at the bottom that for 45 degrees, we have the sine and cosine are both square root of 2 over 2. And for cosine of 135, you have the negative square root of 2 over 2, and the sine of 135 is the square root of 2 over 2. Please satisfy yourself that you can correlate this to the signs of the coordinates in the relative quadrants on the Cartesian axes. Once we substitute these in and simplify, we get our components for vector A and our components for vector B. The resultant is obtained mathematically through direct addition of the components. Since we cannot since we cannot add the vectors directly, it may seem a bit unusual to you that this would be the case, but recall that it is in the movement in a single dimension, 1 plus 1 does indeed equal 2, whereas movement in 2 dimensions, 1 plus 1 need not always be 2. And that is through the relationship of the Pythagorean theorem. However, once we resolve into components, we can add the corresponding components linearly. All x components add together, all y components add together. And so we get our resultant expression as being negative 10 times the square root of 2 in the x direction, and then 30 times the square root of 2 in the y direction, and that gives us this expression. Now we will graph this on a 1 to 10 scale, so each unit marked is actually 10 units in length, and this is so that we can actually get a picture of this here. When we draw our components in the x direction, you can see in orange there, that's the x component of the resultant, and then the pink color there is the y component of the resultant. Please satisfy yourself that the components are indeed pointing in the correct direction, and then the arrow in green is the resultant. And you should go back at this point, let's go back and look and see that indeed we do arrive at a similar picture, although we still do not have any exact numbers as to the orientation of the resultant, we do see that all three methods have indeed led us to a very similar graphical picture. Now, let's determine some specifics for our resultant. First, let's determine the direction of our resultant. And we know that the tangent of theta is given by the y component of the resultant divided by the r component of the resultant, meaning that the tangent of theta is -3, and the inverse tangent of theta. I do need to make one note here. When you punch the inverse tangent of -3 into your calculator, you are going to get a value that's something along the lines of -71.6. Because of the sign changes in quadrants 2 and 3, if your resultant is in quadrant 2 and 3, it is going to be necessary to add 180 degrees to whatever value you get when you take your inverse tangent function. And I have already done that here in obtaining the value of 108.4 degrees. And we should graphically just estimate that real quick on our coordinate plane. If this is your xy axis, beginning at the x-axis, this brings us to 90 degrees. 108 degrees would indeed be approximately where our resultant is. So just recall, if it's in quadrant 1 and 4, we can obtain the inverse tangent function directly. If it's in quadrant 2 or quadrant 3, we have to add 180 degrees to whatever result we get when we take the inverse tangent in order to get the accurate direction of the resultant. The magnitude of the resultant is given through our Pythagorean theorem, and we insert our components accordingly. Execute the squared functions, and you'll get that r squared, or the magnitude of the resultant squared, is 2,000, and when you take the square root of both sides, you will arrive at a magnitude of the resultant at 44.7 newtons. And so in summary, we have a resultant that is given by the expression here at the top that has a magnitude to a considerable degree of accuracy compared to our graphical methods of 44.7 newtons directed at 108.4 degrees. And so you can see that through component form, we arrive at a much more accurate, much more well-defined description of our resultant vector. And so anytime we can resolve components and add them linearly, we're going to get much better results. And we should use our graphical components or our graphical methods to check and give us a good visual picture and determine that use it as a reinforcement that our mathematics is correct. And in this case, we see that we've obtained approximately the same results from 3 different methods, and so we can rest easy that our answer is very likely accurate.